Hey everyone, in Chem 1111 world, it's Dr. Carroll here. This is Unit 4, Lesson 1, Atoms and Light. This is one of my favorite units because we talk about quantum theory, something I did many years ago research on. So it brings back good memories, let's say that. So we're looking at Chapter 4 in our textbook, which is beginning on page 165. 165. And let's write that in there. And now I see my pen. There you go. Page 165. And so we'll be looking at textbooks and PowerPoints to help us look at atoms, the characteristic of atoms. Atoms are small. How about that? Light, because photons, bundles of energy, matter, they talk to each other in the world of spectroscopy. So look at absorption and emission spectroscopy, properties of electrons, quantization and quantum numbers, shapes of atomic orbitals, even a bit about sunlight. Okay, so we're going to see some learning objectives, understand some of the fundamental aspects of atoms, light, atomic spectra, electron energies, properties of free electrons, and those of atoms and molecules, valid sets of quantum numbers, recognize shapes of s, p, d, and f orbitals. Some of you may remember this from other courses. Lasers you can read on your own, characteristics of atoms. This is too much review from back in the day, so I'm going to skip it over here. Yes, I know atoms are small. Let's get to the important stuff here for this particular course. And here we go. So 4.1 you can read on your own. 4.2 is where we get down to business here. So the most useful tool for studying the structure of an atom, what's in an atom, is called electromagnetic radiation, EMR. What we call light is one form of this radiation. We need to know about the properties of light in order to understand what electromagnetic radiation reveals about atomic structure. Okay, so light has both particle and wave properties. It's called the wave-particle duality. Wave-particle duality. Light has wave-like properties. A wave is a disturbance through time. Regular oscillation, which carries energy. Oscillation, vibration, and some particular properties such as up and down variation in position of water waves. That's an example. A surfer waiting for the big one bobs up and down as small ones pass by. Light waves vary with time too. This variation is characterized by the frequency of the wave, frequency nu. So the Greek letter nu is given this symbol, looks like a sort of italicized V with a little hook on it, and the units for that, for frequency, how many crests of a wave pass a point per second, the units are hertz, H-E-R-T-Z, or written as H, capital H, little z, or written as seconds to the -1. Water waves also vary in space. Wave height differs from one place to another. Light waves vary in space. Some of you might remember ripple tank experiments from grade 11. Electric and magnetic potential energy, they vary sinusoidally in electromagnetic radiation, sinusoidally like a sine curve. So you can talk about wavelengths. So the variation in space is characterized by the wavelength. Wavelength, it looks like an upside down Y. It's the Greek letter lambda. That's what we use for wavelength. Some of you in physics might have used F. Oh, sorry, you might have used F for frequency, but that's for mechanical waves. For electromagnetic radiation, we like to use nu instead of F. I mean, if you use F, it's no big deal, but nu is the better one to use. Lambda is the wavelength. Whatever kind of wave we're talking about, it's the symbol for wavelength, and the units are meters. Now you can have metric prefixes. There's also something called angstrom, so there are other variations for the units, but it is the distance from one crest to the adjacent crest, the horizontal distance from one crest to the adjacent crest. That is the wavelength, and as you might expect, the wavelength and the frequency are related to each other. Okay, the height of a wave, that's known as the amplitude. It's given by the letter capital A, and its units are meters. It's the displacement from equilibrium, and it measures the intensity of light, how intense a light is. A bright light is more intense than a dim one. Okay. Light waves always move towards empty space, move through empty space at the same speed, which is the speed of light, 2.998 by 10 to the 8 meters per second. We'll, in this course, just round it to 3 by 10 to the 8 meters per second. And any wave, now if it travels through matter, it's going to be a little less than 3 by 10 to the 8th, but through a vacuum, the speed of any electromagnetic radiation, whether it's a red light or a radio wave or an X-ray, is 3 by 10 to the 8th meters per second. Okay, here's some pictures to help us. We see here wave train there. How many crests pass a point per second is the frequency, wavelength from one crest to the next. So these tops of my train of waves is crests, and any snapshot in time, the bottom called trough. Some of you may have also heard the expressions peaks and valleys, which is okay. From one crest to the next is a wavelength. From one trough to the next is a wavelength. In fact, from any point in phase, if I go through one cycle to another point in phase, that is a wavelength. Amplitude is from our equilibrium point, as if there's no energy disturbance moving through, to the top. That's my amplitude. And you can see here we have, in this first case, we have a wavelength. Here we have a shorter wavelength, which means there's more crests passing some point per second. So the shorter wavelength means a higher frequency, right? Half the wavelength, twice the frequency. Quarter the wavelength, 4 times the frequency. So we see that lambda goes up as frequency goes down. And the product of them, because lambda is meters and frequency is per second, is units of meters per second. And for electromagnetic radiation, that velocity is the constant c. So c can be a big lambda and a little nu, or c can be a little lambda and a big nu, or in the middle. So that's what an inverse proportion means. Oh yeah, there's the amplitude example on the right. There's my equation, c equals lambda nu. The first equation that's going to be helpful with electromagnetic radiation. Okay, let's see. Let's just keep going on here, and then we'll see if the slides give us anything else. So let's say we have an FM radio station and it transmits signals at 88.1 megahertz. Okay, I don't know if there's any radio station in our city that uses that frequency, but maybe. So we're going, what's a radio? What is the wavelength of the radio signal? So c equals lambda nu, so lambda is c over nu. C equals lambda nu, so lambda is c divided by nu. C is the speed of light, 3 by 10 to the 8th meters per second. And nu is the frequency, 88.1 megahertz. Mega is 10 to the 6th. So 88.1 by 10 to the 6th hertz. Okay, so you take 3 by 10 to the 8th divided by 88.1 by 10 to the 6th, and what are we going to get here? 3 by 10 to the 8th divided by 88.1 by 10 to the 6th, 3.40 meters. And there you go. Okay, notice I had to make the conversion. I couldn't leave it as mega because then the units wouldn't cancel out correctly. So I had to remember that mega is 10 to the 6th. Okay? So we're saying that a photon, a little bundle of energy in the radio wave section of the electromagnetic spectrum, has a wavelength of 3.4 meters. Radio waves are known as long wavelength radiation. So I'm going to say, oh yeah, but what about a shortwave radio? Yeah, well that's a shortwave within the radio band. So that is still long wavelength compared to other segments of the electromagnetic spectrum. Okay, so let's try this one here. What is the frequency of light that is a wavelength of 1.4 centimeters? Frequency, so here we're going to have nu is c over lambda. C equals lambda nu, so nu is c over lambda. So 3 by 10 to the 8th meters per second divided by lambda, 1.4 centimeters. Well, we got to convert that to meters. Centi is 10 to minus 2. So 1.4 by 10 to the minus 2 meters. So we get units of reciprocal seconds, which are hertz. So 3 by 10 to the 8th divided by 1.4 by 10 to the negative 2. And I get 2.1 by 10 to the 10th. And those units are hertz, or reciprocal seconds. Okay, or 2.14 by 10 to the 10. Wavelengths and frequencies cover an immense range. What we call light is just a tiny part of the spectrum, what our human eye can detect. And it covers the range from violet, which is around 400 nanometers, to red, which is around 700. And yellow light's somewhere in the center, 580 nanometers. White light separates into the rainbow there as it passes through a prism. There's other parts: gamma rays, X-rays, ultraviolet, infrared, microwave, and radio. You can have short wavelengths, and here we have some examples. They can generate ions, can cause serious damage, and here's all sorts here. So you might remember, if I taught you last year, I had the R-MIVUX-G. Let's see, R is radio waves over here, and then we get into microwaves, infrared, then we got visible, ultraviolet, X-ray, and gamma ray. So this particular textbook writes to me the other way here. So radio, microwave, infrared, visible, ultraviolet, X-ray, gamma ray. And going to the left here, the frequency goes up, and the wavelength going to the left here, so the frequency increases, wavelength decreases in this particular chart. So you see here, these are frequency units, higher and higher frequency, shorter and shorter wavelengths. Gamma ray has the highest energy in the spectrum, long radio waves have the lowest energy, and the highest frequency is gamma rays, lowest frequency is radio waves. Shortest wavelength is gamma rays, longest wavelength is long radio waves. There you go. Look at the small sliver for the visible spectrum there. So yeah, I talked about the energy of the photon, but I didn't actually write it down. So the energy increases as we go from radio waves to gamma rays. Okay, then you see within the electromagnetic spectrum in the visible part that the long wave area is the red and the shorter wave area is the blue-purple, right? So purple photons are more energetic than red photons. It's also helpful, just for a second, let me expand on something, to look at the word sometimes. Infra means below. So below the red is the infrared. Ultra means above. So above the violet is the ultraviolet. So you got infrared, you got the visible spectrum, then you got ultraviolet. Okay? Photoelectric effect, we're going to get to that in a second. We're going to get to that right now. Okay. To help us understand that light are these little bundles of photons, Einstein looked, and I got a Nobel Prize for it in 1905, which is a pretty good year for him, something called the photoelectric effect. And the way it works is you have bundles of light called photons, which have energy called h nu. So I might as well write it right now. Here's the big reveal. The energy of a photon is h times the frequency of a photon. You can also write that as the energy of photon equals hc over lambda, because nu equals c over lambda. So the energy of photon is inversely proportional to the wavelength, because h, which is a constant, known as Planck's constant, and c are a constant, so the product of them is a constant. So the energy and the wavelength are inversely proportional, whereas the energy and the frequency are directly proportional. So you have a bundle of light coming in, it hits a metal surface, and then electrons are kicked out. Okay? When light of high enough frequency strikes a metal surface, electrons are ejected from that surface. That is known as the photoelectric effect. Now, the surprise is it doesn't depend on how long you have the light shining on the metal surface. It depends on the frequency. And that led Einstein to believe, hey, there's got to be these little particles of light which have characteristic frequencies. The frequency has to be high enough to, like ping pong balls coming and knocking out electrons. Once electrons come out, they can create a current in a photocell, or like an electric eye in an elevator is an example. So a detailed study of the photoelectric effect reveals that below a characteristic threshold frequency, nu naught, no electrons are observed, regardless of the intensity of the light. Okay, whether it's dim or whether it's bright, if you don't have enough frequency for your incoming photons, you are not going to eject electrons. Above the frequency, then the greater the frequency of the incident light, the greater the maximum kinetic energy. Okay, and above the threshold frequency, the number of emitted electrons increases with the intensity, but the kinetic energy per electron does not depend on the intensity. Okay, so that's another detail of it. And usually it's metals which are involved with the photoelectric effect. And so Einstein provided the explanation by talking about light coming in these little bundles called photons, and the energy of a photon is h times the frequency. Planck's constant is named after Max Planck, who was one of the founders of quantum theory. Introduced this concept in 1900. That was a long time ago, wasn't it? And the value for Planck's not prank, that's it. You'd be, I don't know, playing a joke on someone. Planck's, you don't have to memorize it, but the value for Planck's constant is 6.626 by 10 to the minus 34 joule seconds. That's the units. It's joules times seconds because frequency is seconds to the minus 1, so the seconds to the minus 1 and the seconds cancel, and you get joules. Some books put a little dot between the joules and the seconds, some don't. ICR's doesn't, but you can if you want. And most people just round it off to 6.63 by 10 to the minus 34 joule seconds. I think Planck's constant was used in an episode of Stranger Things, or some secret code or something. Anyways, let's try an example together and then a practice exercise. Well, let's try that one together too, and then try some photoelectric effect calculations. So what's the energy of a photon with red light of wavelength 655 nanometers? And let's also get the frequency while we're at it. So 655 nanometers is going to be 655 by 10 to the minus 9 meters. Now if you punch that in your calculator and press equals, it may convert it into standard scientific notation. So be careful about that. You know, it's not like, oh, it's a whole new number. It's just expressed in a different way, right? Let's see what happens on my calculator. If I hit 655 by 10 to the negative 9, oh, it goes into standard, or goes into common notation without any scientific notation. Let me hit second scientific, 6.55 by 10 to the minus 7. So 655 by 10 to the minus 9 meters is also 6.55 by 10 to the minus 7 meters. Okay, energy is h times nu. So, but here we're given the wavelength, and nu is c over lambda, so I said energy is hc over lambda. So Planck's constant, speed of light, there's my nanometers to meters, and I get 3.03 by 10 to the minus 19 joules. So one photon of red light has an energy of 3.03 by 10 to the minus 19 joules, which you might think is small, but it's comparable to energies of chemical bonds. And if I want to do a mole of these red photons, it's 182 kilojoules per 1 mole. If I want to get the let's get the frequency. Well, we have it here. Why not for some practice? So nu is c over lambda. So it's 3 by 10 to the 8th meters per second divided by lambda 655 by 10 to the minus 9 meters. So that cancels. So I get 3 by 10 to the 8th divided by 655 by 10 to the negative 9. And I get 4.58 by 10 to the 14 reciprocal seconds. Or hertz. Okay? Let's try this practice exercise together here. What is the energy of an ultraviolet photon whose wavelength is 254 nanometers? Okay, you don't have to memorize the numbers associated with the ranges in the spectra. I've seen some textbooks that do that. I said, no, you don't have to do that. Okay, on a test, I could just say, what's the energy of a photon of 254 nanometers? And you calculate it. I won't ask, just out of the blue, what section of the electromagnetic spectrum is 254 nanometers. That would be sort of nasty. So E equals hc over lambda. So h, I'm just going to round off, 6.63 by 10 to the minus 34 joule seconds. C, 3 by 10 to the 8th meters per second. And then lambda, 254 nanometers, so 254 by 10 to minus 9. And you do that, and I'll just write out the answer here. 7.82 by 10 to minus 19. Remember, with these screencasts, you can pause them at any time, right? And do the question, and then make sure you're right. And you can, you want to get the frequency, go ahead, and U is C over lambda. So it'll be, it wasn't asked, but let's get it anyways. 3 by 10 to the 8th is C divided by lambda, 254 by 10 to the negative 9. 1.18 by 10 to the 15. And that is units of reciprocal seconds. Okay, so now let's talk a bit more about that photoelectric effect and the energy balance. Here you have photon energy, and you have the binding energy or the threshold energy on the metal, and once the photon comes in, some of that energy is used to knock the electron out, and any excess has kinetic energy. Kinetic energy, remember, is 1/2 mv squared classically, okay? So we see here in symbols, the ejected electron kinetic energy is the incoming photon energy. Energy is h nu minus the binding energy, which is h nu naught, the minimum amount of energy needed to knock the electron out. Okay, and then that paragraph, I've already mentioned that, you can read it again. Let's try an example of how this works. So example 4.4. If I have a potassium is K, to kick an electron out, the threshold energy, or minimum energy, h nu naught, is 3.7 by 10 to minus 19 joules. If I have some photons, red photons, 4.3 by 10 to the 14 hertz, and blue photons, 7.5 by 10 to the 14 hertz, will they cause a photoelectric effect to happen? And what's the maximum kinetic energy of the ejected electrons? Okay, so we must analyze the energy requirements. No electrons will be ejected unless you have overcome the threshold. Okay, so the threshold energy is 3.7 by 10 to the minus 19 joules. The red photons, h nu, 6.63 by 10 to the minus 34 times 4.3 by 10 to the 14, that is the characteristic frequency for red light, I get 2.8 by 10 to the minus 19. For blue, 6.6 by 10 to the minus 34, oh, it's higher frequency, higher energy, so you get 5 by 10 to the minus 19. So shining red light all day long on the potassium metal will not cause ejection of electrons from the potassium metal surface, because 2.8 by 10 to the minus 19 is less than 3.7 by 10 to the minus 19. However, blue light will because you have more than the threshold. You have 1.3 with 10 to the minus 19 molar. Okay, so the excess kinetic energy is carried off by those ejected photoelectric electrons, 1.3 by 10 to the minus 19. And if I want, I could then get the speed of the electron, because I got 1.3 by 10 to the minus 19 joules, so 1/2 mass speed of the electron squared. I'm not going to do that here. I don't think the book asks for that very often, but I could get the mass of the electron and then divide half the mass into the energy, take the square root, and there's the speed. Okay, let's try, will green photons work? Well, let's see, Roy G. Biv, blue worked, red didn't, green is right, let's see, 515, which is, well, we have to figure it out. We were given frequencies of the other colors. Here we're given a wavelength. So let's get the energy for the green. So it's h nu, but nu is c over lambda. So hc over lambda. So let me just punch it out here, and I'll say it as I do that. 6.63 by 10 to the negative 34 times speed of light, 3 by 10 to the 8th, divided by lambda, 515 by 10 to the negative 9. And I get 3.86 by 10 to the negative 19. Now, what was my minimum threshold again? Minimum threshold was 3.7 by 10 to the minus 19. So this is 3.9 to 1 decimal. So yes, it will. And the difference will be, yes, would be 3.86 by 10 to the minus 19 minus 3.7 by 10 to the negative 19, which is 1.6 by 10 to the minus 20. I see the answer to the back of the book say 2, so they're rounding to 1 sig fig, but 1.6 by 10 to the minus 20. I'm not going to make a big deal about sig figs, but sometimes on some of the assignments you do with numerical answers in your computerized assignments, you'll have to make a bigger deal about sig figs. Okay, so photoelectric effects show that light has some properties of particles, and there's also some properties of light that behave as waves, diffraction, interference patterns, etc. And same with electrons. Electrons can behave as waves, electrons can behave as particles, depending on what you're looking at, what properties you're talking about. Okay, section exercises, those you can try on your own. And then we get to absorption spectra. That'll be our second lecture. Let's just see if there's something from the slides that'll help us. Okay, so there's ones. I'm just going through, it's probably repetitive here. But there's some definitions. Where light has wave aspects, wavelengths, frequency, amplitude. Okay. Speed of light, the examples. Most of these slides are just photos. There's the electromagnetic spectrum, images from the textbook, photoelectric effect. I mean, sometimes there's a bit more information. Light's wave has particles, the phenomena of photoelectric effect. Energy photon collides with an atom, ejecting an electron. Okay, Planck equation, we looked at that. Okay, some examples. There's my kinetic energy. That's the example we just did. And so that's good for our first lecture on Unit 4.